in an ideal world, all our devices should be perfect. And for example, steady flow devices should be isentropic. So isentropic process is the perfect ideal process through such devices. So an ideal turbine is an isentropic turbine. An ideal pump and compressors are isentropic compressors and pumps, okay? But we know that in real life is not the case. So we know that our systems, turbine, pumps, and compressors are not isentropic, are not perfect. So the question now is that how to take into account the deviations from an isentropic process, okay? So how to quantify this deviation from ideal perfect process. For this, we'll be using the concept of isentropic efficiencies, okay? So this is why we'll be covering now isentropic efficiencies for steady flow devices. We will split this into two. From one side, we will be considering turbines, providing us with work out, and from another side, we'll be considering compressors and pump. And you will see the difference, okay? So let us sketch the process through a turbine, okay, on a specific diagram that we'll be calling HS diagram. Enthalpy, entropy, okay? We have here a turbine. Can be a gas turbine or a steam turbine. We have the shaft work. We have here entry in state 1 and leaving at state 2. And this is our turbine. So we know that the enthalpy at the inlet should be higher, okay? So we have here our state 1. Now, what is state 2? If it's perfect, ideal, adiabatic, and reversible, so therefore isentropic, we are expecting state 2 to keep the entropy constant, so therefore it's a vertical line, bringing us here. This is state 2, okay? But there is nothing like an isentropic turbine. In real life, turbines are not isentropic, okay? So as a consequence, they will be increasing the entropy, leading us to a second point here, 2. Okay, so this one, 2, we'll write it as 2s, okay? Why 2s? Because this is the state where s is constant, isentropic. And this one, we can keep it as 2, or sometimes it's called 2a for actual, okay? So this a is actual. And this s is because s remains constant. So in an ideal perfect world, you are going straight down on an HS diagram, but in reality, you are increasing entropy, okay? The analogy I will be giving you here is that we all watch, for example, movies where somebody who is driving and let's say a drunk person arrested by the police, and this person is asked to walk on a straight line. So basically, if this person is walking down this line straight, so our conclusion is that this person is not drunk. But if this person starts basically deviating from the straight line, so it's imperfect, so we'll consider that this person is drunk, okay? So in our case, hopefully, however, is that the processes in this direction for a turbine are not allowed, because those are processes that will be decreasing in entropy, okay? So here, this means that we have two types of work. We have the ideal work, if it's isentropic, and we have the real work. We will be using an isentropic efficiency, eta, isentropic, is equal to the ratio between the work and another type of work. Well, what do we know is that we know that this efficiency should be lower than 1, okay? Lower or equal if it's isentropic. And it's the ratio between two works. So now we have to ask ourselves the following question. If we are given the actual work, the real one, versus the work isentropic, well, which one is the highest? Isentropic is perfect. So when your turbine is working and following an isentropic process, it giving you the maximum work you can get. So the isentropic work is higher than the actual work, because the actual work also, you have irreversibilities. You have heat losses, you have friction, you have energy losses when the flow crosses your blades and so on. So this term is higher to have the isentropic efficiency lower than 1. So therefore, it's isentropic over actual. Okay? Now, we can write it again as isentropic for a turbine is equal to what? Now the actual work is H1 minus H2. So this is this path, okay? H1 minus H2 or H2A. And the isentropic work is H1 minus H2S, okay? So it's basically the ratio of this length over this length, okay? And give you a basic an idea on the tangent of this angle. Call it alpha. Okay? So this is how we'll be characterizing a non-isentropic turbines, non-ideal turbines. Okay? Typically, we will see that the isentropic efficiency of the turbines that we'll be analyzing are around higher typically than 80%. So meaning that our turbines are kind of 80% ideal. Okay? Now, if we apply the same concept to compressor and the pump, we will be sketching the same HS diagram. Now it's different because a compressor and a pump will be increasing their enthalpy. You increase the enthalpy through a compressor and pump. So we start here. And again, if it's ideal, it's isentropic, going straight up, and giving us this point, which is 2S. But since our compressors and pumps are not ideal, they increase the entropy, leading to state 2 or 2A actual. So this is the ideal, and this is the actual. So the same way we can write that for the isentropic efficiency. Now for a pump isentropic, pump or compressor. So basically what I'm saying here, devices where you provide work to the system, okay? And not like a turbine where the system is providing with work. It's equal also to a ratio of two types of work. Work and work. And we know again that this has to be smaller or equal than 1. So we ask ourselves the same question. We have the work, which is actual for a pump or a compressor, and we have the work isentropic. Which one is the highest? Here we have to be careful, because here we are providing work to the pump and the compressor, okay? In an ideal world, we should provide less work because you are plugging your pump and your compressor to the outlet, you are paying electricity, and therefore you are paying, for example, here Hydro-Quebec. So in this case, the ideal case for you is to provide less work. So the isentropic work is the minimum work you have to provide to your pump or your compressor to change your state from 1 to 2, okay? So meaning that the isentropic work is smaller than the actual work. In real life, unfortunately, because of all irreversibilities, again, friction, pressure losses, viscous losses, you will have to provide more work to your pump and compressor than required. So, and now because we have this one is the smallest. So here we can write, this is isentropic, so it's the inverse of this one, over actual. Okay? So this means that we can write now for the isentropic efficiency for a pump or compressor, we can write it as, well, what's the isentropic work? This is this one, right? It's H, we can write it actually H1 minus H2S over the actual one, which is H1 minus H2, okay? So you can flip them. You can write H2S minus H1 as long as you also flip the bottom H2 minus H1, okay? So this means that here we define the isentropic efficiencies for turbines, and here we have the isentropic efficiencies for compressors and pumps, okay? And this will give us an idea on if we have non-ideal flow devices, steady flow devices, how to account for this deviation from the isentropic ideal process.